Here's our first definition for speed. Speed is the distance travelled by an object in 1 second. You can use this equation to help you work out the definition for speed v. d is the distance travelled and t is the time in seconds. Next, we've got velocity. Velocity is the displacement of an object in 1 second. Here's a similar equation that helps, although this time v is velocity, s is the displacement of the object, and again t is time in seconds. Acceleration. Acceleration is the change in velocity in 1 second. The equation to use this time is that acceleration a is equal to v minus u divided by t. U is the initial velocity of the object, and v is its final velocity. So v minus u is the change in velocity, and t is time in seconds. Kinetic energy. The energy an object has due to it moving, which depends on the object's mass and velocity. And of course, this is the equation which allows us to calculate kinetic energy. Potential energy. The stored energy of an object when it's lifted a height h above ground level. And this is the equation for potential energy, where g is gravitational field strength, 9.8 newtons per kilogram on Earth. And that just happens to be our next definition. So gravitational field strength is the weight of 1 kilogram. We can use the equation W is equal to mg to help with this one, but rearrange to make gravitational field strength g the subject. To do this, divide both sides by m. W is weight in newtons and m is mass in kilograms. So the gravitational field strength on a planet is just the weight of 1 kilogram on that planet. Scalar. A scalar quantity is a quantity with magnitude or size only. And no surprise that the next definition is vector. A vector quantity is a quantity with magnitude or size and direction. And here's a little test for you. In a few seconds, the oval shape will disappear and each quantity will either move to the left if it's a scalar or right if it's a vector. Where does each quantity belong? Distance, speed, mass, time and energy are scalars, while displacement, velocity, force and acceleration are vectors. Next up, we have balanced forces. We say that forces are balanced when the forces acting on an object are equal in size and opposite in direction. And here's an example of balanced forces. This, however, is an example of unbalanced forces. We'll end the video by going over Newton's laws. Here's the first. Newton's first law states, when the forces acting on an object are balanced, the object will remain at rest or continue to move in a straight line at constant velocity. Newton's second law, however, deals with unbalanced forces. When the forces acting on an object are unbalanced, the object will accelerate. We can also say that the object's acceleration is directly proportional to the unbalanced force acting on it. Here's the equation that links unbalanced force and acceleration. If we divide both sides by mass m, then we can make acceleration a the subject, like this. So acceleration a is equal to the unbalanced force F divided by mass. You should see then that the acceleration is directly proportional to the unbalanced force. And finally, here's our last one, Newton's third law. It states that if A exerts a force on B, then B exerts an equal force on A in the opposite direction. Newton's third law often crops up in questions about rockets. The rocket exerts a force on the exhaust gases in one direction, and the exhaust gases exert an equal force on the rocket in the opposite direction. You should actually be able to describe the Big Bang in simple terms, but here's the definition. The Big Bang is a theory for the formation of the universe which occurred around 13.7 billion years ago. Next, we've got 10 terms which you're expected to be able to use correctly and in context. Knowing the definitions will help you to do this. Here's the first. Planet. Since poor old Pluto was demoted in 2006, we've had to update our definition for what we call a planet. This is it. A planet is a celestial body That's a natural object located outside of Earth's atmosphere, in orbit around the Sun, with a nearly round shape which has cleared the neighbourhood around its orbit and is not a satellite. As I said, we only need to use the word planet and the following 9 terms correctly. We'd not be expected to remember the definition. You should remember though that our solar system contains 8 planets. You can work out the order from the Sun by remembering my very easy method just speeds up naming. Now, I mentioned Pluto before, and of course it's now classed as a dwarf planet. A dwarf planet is a celestial body in orbit around the Sun with a nearly round shape, which has not cleared the neighbourhood around its orbit and is not a satellite. Pluto is a dwarf planet together with 4 others, although there could be hundreds out there waiting to be discovered. Moon. A moon is a celestial body that orbits a planet. Sun. Of course, the Sun is the star at the centre of our solar system. And, talking of stars, a star is a ball of gas which produces heat by nuclear fusion. If you're counting, then you'll know that that was the 5th in a list of 10 terms that you're expected to use correctly. Here's number 6. Asteroid. When I was a teenager, all I knew about asteroids was that it was an amazing computer game together with Space Invaders. Now though, as a physics teacher, I know that an asteroid is a small rocky object which orbits the Sun. The solar system. This is made up of the Sun and all the smaller objects which orbit it, including the 8 planets and their moons. An exoplanet. These are also known as extrasolar planets, which gives us a clue as to what they are. An exoplanet is a planet outside our solar system that orbits a star. Galaxy. A galaxy is a system of billions of stars, gas and dust, held together by gravity. And finally, here's the 10th term that we're asked to use correctly and in context. Universe. The universe is basically everything, all existing matter and space. Moving on from our list of 10 terms then, we have light year. This is an important one because as well as knowing what the term means, you'll need to also be able to convert distance from light years to meters. So a light year is the distance travelled by light in 1 year. This probably isn't the video to show you how to convert light years to meters though. I'll go on then. So we use this equation, distance d equals speed v multiplied by time t. That gives us 3 times 10 to the power of 8 multiplied by 365 times 24 times 60 times 60. If you're not sure where these numbers come from, that's the speed of light multiplied by the number of days in 1 year times the number of hours in 1 day times the number of minutes in 1 hour times the number of seconds in 1 minute. That means that 1 light year is equal to 9.46 times 10 to the power of 15 metres. The important thing here is remembering how to convert light years to metres, not the number itself. This is our final definition, geostationary satellite. The important things to remember here are the period of the satellite, that's the time taken for it to orbit the Earth, and its height above the Earth's surface, its altitude. So a geostationary satellite is a satellite with a period of 24 hours orbiting the Earth at an altitude of 36,000 kilometres. To end the video, we'll look at some diagrams. Here you'll have to identify the name of each type of spectra. First off, we have a continuous emission spectrum. The diagram in the middle is known as a line absorption spectrum, and the bottom diagram is a line emission spectrum. If you want to learn more about how various spectra are produced and the information we can gain from them, then take a look at this video. Here's the first definition, current. Remember that you can pause the video once the term is displayed to give yourself more time. Current then is the charge transferred in 1 second. You can use this equation to help you work out the definition for current, I, although you'll need to rearrange it to make I the subject. Just divide both sides by time t. Now we can see that current I is equal to charge q divided by time t. The unit for time is of course the second. So current is, as I said earlier, the charge transferred in 1 second. Next up we have voltage. If you have a good understanding of the difference between current and voltage, then you'll understand why voltage splits in a series circuit, but it's current that splits in a parallel circuit. The voltage of a power supply, then, is the energy given to each coulomb of charge by the power supply. There is a higher physics equation which helps us with this definition, but we'll stick to National 5 for now. Next up is power. Let's see if you can work out a definition for power using an equation. The equation links power, energy and time. And remember that the unit for time is seconds. This is the definition. Power is the energy transferred in 1 second. And this is the equation which helps you to work it out. Power P is equal to energy E divided by time T. That's it for the electricity definitions. I told you this video would be short. So all we have left is to identify which of the following oscilloscope traces is AC and which is DC. Here's the first. And, wait for it, here's the second. The first one is, of course, AC, which stands for alternating current. The oscilloscope basically displays a graph of voltage on the y-axis against time on the x-axis, with this central horizontal line representing 0 volts. The AC trace is both above the line, positive, and below the line, negative. The second trace, however, is DC, direct current, because it's entirely above the central line, although this trace would also be DC, as it's entirely below the central line. If you look at this new trace on the oscilloscope on the left of the screen, you should be able to work out that it too is DC. The trace is altering in size, but again it's entirely above the central line. Pressure. In this video, 4 out of the 5 definitions can be worked out from an equation, and this is one of them. So, pressure is the force exerted on 1 square metre. And this is the equation which can help you remember that. Pressure P is equal to the force F divided by area A, remembering that the unit for area is the square metre. Next up is the one definition in this video where an equation isn't used to remember it. Temperature. Here you'll just need to know that the temperature of a substance is a measure of the mean or average kinetic energy of its particles. Specific heat capacity. This is related to heating a substance, resulting in a change of temperature. Specific heat capacity is the heat energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. This is a difficult one to remember, although this equation should help. To make specific heat capacity C the subject of the equation, you have to divide both sides by m delta T, like this. Specific heat capacity C is equal to heat energy, EH, divided by mass m in kilograms, multiplied by change in temperature, delta T, in degrees Celsius. Make sure that you can see the link between the equation and the definition before moving on. Here's the next one, specific latent heat of vaporisation. This one is again related to heating a substance, although since the substance is at its boiling point, it results in a change of state. Here's the definition. The specific latent heat of vaporisation is the heat energy required to change 1 kilogram of a substance from a liquid at its boiling point to a gas. This equation should help you to work out the definition as long as you remember the change of state. To make specific latent heat of vaporisation L the subject of the equation, divide both sides by m. EH is heat energy and m is mass in kilograms. The same equation can be used to help us work out a definition for specific latent heat of fusion. The only change is that this relates to a change of state from solid to liquid. So specific latent heat of fusion is the heat energy required to change 1 kilogram of a substance from a solid at its melting point to a liquid. Refraction. Refraction is the change in speed of light as it passes from one material to another. This diagram shows a glass block in air. Here we can see the light bend towards the normal, the dotted line, as it passes from air to glass, and away from the normal as it passes from glass to air. Although light doesn't always change direction during refraction. If the light has an angle of incidence of 0 degrees, in other words straight along the normal line, then there's no change in direction and the light passes straight through. What is happening though is that the light is changing speed. 3 times 10 to the power of 8 meters per second in air and 2 times 10 to the power of 8 meters per second in glass. These values are given in the examination's datasheet, so there's no need to remember them. Next up, we have diffraction. The important difference here is that there's no change in the speed of the wave, and the wave isn't passing from one material to another. Diffraction is the bending of waves at a gap, as shown in this diagram, or obstacle, as shown here. Make sure that you also know how the wavelength of the waves affects how much diffraction takes place. Our next definition is transverse wave. Watch the animation, which should help you remember the definition. Here we have a water wave moving from left to right. The blue dot indicates the position of a single drop of water making up the wave. As you could see, the wave direction was from left to right, although the motion of the drop of water was up and down. So a transverse wave is a wave in which the particles of the medium, water in this example, vibrate at right angles to the direction the wave is travelling in. As I said earlier, water waves are transverse waves, as are all electromagnetic waves, light, microwaves, radio waves, and so on. Next, we have longitudinal waves. And again, there's an animation. Here it is. This time, the animation represents a sound wave. Again, the wave direction is from left to right, as indicated. The red dot here represents an air molecule which vibrates from left to right. In other words, parallel to the direction of the wave. A longitudinal wave is, therefore, a wave in which the particles of the medium, air in this second example, vibrate parallel to the direction the wave is travelling in. And that's the final definition. We'll end the video by identifying some wave characteristics using the following diagram. First off, we have the crest of the wave, followed by the trough. Hopefully you should see that there are 4 waves in this diagram. The distance from one crest to the next is one wavelength, although it could be measured between these 2 points, or from one trough to the next, like so. Finally, the distance from the centre of the wave up to the crest is known as the amplitude. We'll begin by looking at the 3 different types of nuclear radiation. Our first definition is alpha particle. An alpha particle is a helium nucleus, ejected from an unstable nucleus. Alpha particles are positively charged, move at roughly 5% of the speed of light, and are the most ionising type of radiation. Next up, we have the beta particle. Nuclear radiation is emitted from the nucleus of an atom, although you wouldn't expect to find a beta particle there. A beta particle is a fast-moving electron ejected from an unstable nucleus. Beta particles are emitted when a neutron in the nucleus is converted into a proton and an electron. Beta particles are negatively charged, move at around 90% of the speed of light, and are moderately ionising. Finally, we have the gamma ray. These are not particles, but are in fact a high-frequency electromagnetic wave ejected from an unstable nucleus. Gamma rays travel at the speed of light and are very weakly ionising. Talking about ionisation, that's our next definition. So, ionisation is the addition or removal of an electron from a neutral atom, leaving it charged or ionised. The next animation shows how a positively charged alpha particle can remove an electron from a neutral atom. In this case, the atom would then be positively charged. Let's watch. As I said, as the negatively charged electron is removed from the neutral atom, it's then left positively charged, a positive ion. Our next definition is activity. Like many of our previous definitions, there's an equation which goes with this. Activity is the number of nuclei that decay in 1 second. The equation to help remember this one is A is equal to N divided by T. A is activity in becquerels, N is the number of nuclei decayed, and T is time in seconds. Half-life. Now, if you'd like to know how to calculate the half-life of a radioactive source, then why not take a look at this video. As for the definition, you'll need to remember that the half-life is the time for the activity of a radioactive source to decrease by half. Now we have radiation weighting factor. There is an equation which includes this, although it will not help with the definition, which is that radiation weighting factor is a measure of the biological effect of a radiation. Next up, it's fission. Maybe the animation will help us remember this one. Fission is the splitting of a heavy nucleus into two smaller pieces, and 2 or 3 neutrons. Now, I know what you're thinking at this point. What would happen if each of those neutrons emitted in the fission reaction goes on to cause further fission reactions? Well, in that case, we'd have a chain reaction. A chain reaction is when neutrons released in fission cause additional fission reactions to occur, and so on, and so on, and so on. Last up, we have fusion. Why don't we watch this animation first, which should help jog our memories. So, a fusion reaction is the joining of two nuclei to form a new, heavier nucleus. And that, as they say, is that. If you've not already subscribed, then please do so. That way, you'll be kept updated as new videos are released.